us, the universe has long captivated us with its immense scale of distance and time. How far does it extend, where does it end, and what exists beyond the stars and galaxies stretching to the limits observable by telescopes? These questions are opening up numerous new research directions, particularly technologies that allow us to observe not only the most remote regions of the universe, but also the behavior of matter and energy at microscopic scales. Notably, the deepening understanding of the subatomic world inside the atomic nucleus now allows us to glimpse answers to the ancient question, how vast is the universe? In ancient times, most observers considered stars as a sphere enveloping the earth and the dwelling place of gods. The Greeks were the first to view astronomical phenomena as natural events, subject to human exploration rather than the whims of deities. A sky observer named Anaxagoras suggested that meteors were composed of earthly material and could even originate from Earth. These pioneering astronomers laid the foundation for modern science, but they would be astonished by the discoveries of their descendants today. Stars and planets once considered abodes of gods are now seen as incredibly tiny particles within a vast system of matter and energy spread throughout space. A turning point came in the 1920s with the giant 100-inch Hooker telescope on Mount Wilson, California. Astronomer Edwin Hubble and his assistant Milton Humason analyzed light from faint patches called nebulae. They proved these were actually distant galaxies beyond our Milky Way. Hubble and Humason discovered that most of them are moving away from us. The more distant the object, the faster it recedes. This fact, now called Hubble's law, suggests there must have been a time when matter from all galaxies was concentrated at one point. Everything astronomers see through increasingly larger telescopes originated from a single beginning, now called the Big Bang. The expansion of the universe was predicted by Albert Einstein in 1917. But even he didn't believe it until he saw the evidence from Hubble and Humason. Einstein's general relativity suggests galaxies move apart because space itself is expanding. When photons emitted from a distant star travel through the ever-expanding cosmic space, it increases the distance to reach us. Therefore, the size of the universe since the Big Bang depends on the expansion time and its rate. Recent precise measurements from the Hubble Space Telescope and other instruments confirm the universe is 13.8 billion years old. In that time, light travels 13.8 billion light years, equivalent to 1.3 billion kilometers. But considering expansion, the most distant galaxy detected by Hubble is actually 46 billion light-years away from us in each direction, with a total distance of nearly 92 billion light-years. So is that the size of the universe? Not exactly, according to a new theory describing the origin of the universe. Our 92 billion light-years is just a speck of dust in the entire universe. The theory is based on the discovery that energy continuously escapes from the vacuum of space in the form of oppositely charged particles, matter and antimatter. In the 1980s, physicist Alan Guth proposed that the energy field in the vacuum suddenly shifted to a high-energy state, causing space-time to literally inflate. The universe transitioned from atomic size to cosmic size in an extremely brief moment. According to Guth's calculations, the overall universe would be 10 to the power of 25 times larger than the observable universe. In other words, the entire universe compared to the observable universe is like the observable universe compared to an atom. The extremely rapid expansion of the universe helps explain its enormous size and homogeneity. But to be successful, the theory must also explain how the universe created everything around us. All stars, galaxies, galaxy clusters, and ultimately ourselves. Early days by creating what? At Brookhaven National Laboratory in New York, they collide gold atoms head-on in a nearly 2.5-mile-long tunnel. When these atoms reach near light speeds, they collide violently, creating an exploding fireball. Reach temperatures exceeding 2 trillion degrees Celsius. According to current understanding, the last time our universe was this hot was a millionth of a second after it formed. What captures scientists' attention is the bombardment of subatomic particles, a superhot mixture of quarks and gluons, believed to have created matter as we know it. In early experiments, this quark-gluon plasma exhibited a crucial property: low viscosity or low resistance to flow. Scientists call it a perfect fluid. To understand its importance, we go back to the primordial energy fields thought to have produced the Big Bang. It is believed that these fields contained small fluctuations that were amplified to a large scale during the inflationary period. In the extremely dense quark-gluon mixture, these fluctuations generated pressure waves or shock waves. As the universe expanded, these shock waves caused variations in matter density. Surprisingly, traces of those primordial shock waves still exist today as faint signals accidentally detected in the 1960s. Working for Bell Telephone Company, physicists Arno Penzias and Robert Wilson built a giant horn-shaped antenna. But no matter where they pointed it, the device picked up excessive noise in the microwave band of the electromagnetic spectrum. That noise turned out to match a prediction made years earlier. That after the Big Bang, the universe was filled with an extremely hot gas cloud that scattered all light. As the universe cooled, the cloud dissipated and light could pass through. Over time, the spectral signature of this light shifted as the universe expanded and cooled, to the point that Penzias and Wilson detected what they heard, believed to be the echo of the Big Bang. This image shows the smooth contours of the light recorded by the Bell team. Scientists would have to look more closely to find traces of cosmic inflation. The Space Shuttle Discovery launched the Hubble Space Telescope into orbit on April 24, 1990. In one of the most significant scientific milestones of our era, another launch, considered equally important, occurred 5 months earlier. The Cosmic Background Explorer, abbreviated as COBE, was launched to observe more closely the microwave radiation detected by Penzias and Wilson. Results after 2.5 years showed that the light of the early universe contained a pattern of hot and cold spots. In this image, nothing less than the origin of everything we see around us today. Smooth on a large scale, but with significant clusters from which gravity would form gas clouds. Then stars and galaxies. With this model of the universe, astronomers began exploring how the patterns and sizes of the universe evolved over time. In the era of computer-controlled telescopes and automated observations, astronomers can now initiate large-scale international collaborations, with the goal of mapping a large portion of the universe in 3 dimensions. At Apache Point in New Mexico, the Sloan Digital Sky Survey set the standard for mass production astronomy. Multiple steel plates are drilled with holes precisely matching the positions of galaxies in the night sky. After plugging fiber optic sensors into the holes, these plates collect light from hundreds of galaxies each night. From that light, astronomers calculate their distances to Earth. Another survey called the All-Sky Survey. High micron are mines, based on the infrared light frequency that its detectors are tuned to record. In this image, high micron data covers an area 60 million light-years wide. The local group of galaxies, including the Milky Way, is located at the center. This is our intergalactic neighborhood. Let's go further to an area about 200 million light-years wide. Our location is linked to the dense Virgo supercluster. The nearest intergalactic city opens up an area over 320 million light-years wide. You can see the full width of our local cosmic region. Galaxies arrange into walls and arcs. Out there are sparsely populated regions, the countryside of the universe. In the data, this region has a width of over 650 million light-years, followed by nearly 2 billion, 3.2 billion, and finally an area spanning 6.5 billion light-years in the cosmic continent. Amidst all, our galaxy, though vast from an earthly perspective, is as small as a speck of dust. The HIMSS study, SLAN Digital Sky Survey, and Galaxy Redshift Survey. Two telescopes in Australia expanded our map to a portion from the early universe. They charted a grand cosmic roadmap. The successor to COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched to scan the early universe for the origins of this cosmic atlas on a small scale. WMAP moved beyond all interference from Earth to a balance point between Earth and the Sun. There, for 2 years, its detectors collected primordial light from deep space. This is what WMAP saw, a pattern matching the filaments and voids that developed in the universe. Scientists are studying WMAP data for clues to the actual size of the universe. For example, one team searched for repeating patterns, which could be evidence of pressure waves bouncing back through the hot gas of the early era. They found nothing, implying the universe had grown so large during inflation that such waves could not traverse it. Then they calculated and reported that the entire universe must have a minimum diameter of 78 billion light-years. So what is its maximum size, and how does it exceed that? We will never know for sure what lies beyond our direct view. But astronomers are making surprising suggestions about the universe they can observe. To ancient observers, the universe was composed of 5 classical elements: earth, water, air, fire, and the 5th element, quintessence or space. Aristotle believed that the unchanging and incorruptible stars were made of this 5th element. Today, in fact, we find that space has a unique characteristic. Astronomers have calculated the gravity needed to bind stars as they orbit galaxies, or galaxies as they orbit galaxy clusters. They discovered there isn't enough visible matter to hold these structures together. The missing component, identity unknown, they call dark matter. In supercomputer simulations of the universe's evolution, dark matter is added to provide the necessary gravity to form the web-like pattern with filaments and walls, voids and dense clusters that we see in the universe. But something else is happening on this large scale. Astronomers are making precise measurements of the universe's expansion rate using a new type of distance marker. They want to know if gravity is slowing the universe's growth rate. The markers they use are type 1a supernovae, thought to have uniform brightness across the universe. By measuring changes in the brightness of these standard candles at different distances, researchers can detect changes in the universe's expansion rate. To their surprise, the data showed the entire universe is not only expanding but accelerating outward. The culprit is believed to be energy bubbling up from the cosmic vacuum, similar to the Big Bang era, causing cosmic inflation. By appearing in small amounts everywhere, it is pushing space outward across the entire universe. Over time, this so-called dark energy has grown to an astonishing extent, accounting for 3/4 of the total matter and energy in the universe. With data like this pointing to a fundamental force in our universe, some scientists are thinking about the universe in broader terms than ever before. For example, there is a version of inflation theory that suggests we live in one of many universes, possibly coexisting side by side but not touching. Like bubbles, they continuously emerge and spread across the endless ocean. Just 500 years ago, in Galileo's time, many looked into space and saw a universe of light centered on Earth. The invention of the telescope revealed stars far beyond our planet. Then came galaxies, galaxy clusters, and beyond, vast walls and clumps of matter. New ideas about the size of the universe have created a leap in our perception of scale. By extending these structures far beyond our sight, do these discoveries make us feel small on this alien planet and in an increasingly shrinking corner of the universe? Or does the ability to understand and imagine the distant limits of time and space somehow expand our significance in the grand picture of everything?